Alrighty, AP Chemists, this is our summer work, important information part 4. This should be our 5th and final lecture for limiting reactant. I'm going to start us off with looking at this conceptual limiting reactant and theoretical yield with pictures. Maybe you were able to think about it and compare this to the sandwiches. Then I'm going to carry and do about 2-3 more examples and leave you to do the exercises on your own to turn in, right? So you just need to turn in the exercises 13 through goes all the way to, I believe, 19 for full credit. And then I want to make sure that you notice, you might not have seen this since the end of part 3, but at the very end, I have a preparing for basics quiz set of questions. Remember, in the beginning of the school year in September, we will do a little bit of review, and then you will need to take a basics quiz on all of the summer work. If you answer these 6 questions, you are preparing for the basics quiz. These are sample questions that are very similar to what will be on your basics quiz. So being able to answer these questions are going to be super helpful. Alrighty, so let's just get into it. Let's go back to the conceptual question here. So here's this chemical reaction. I said I have the synthesis of ammonia. For every 1 mole of N2, I need 3 moles of H2, and I'll make 2 moles of NH3. So I have to think to myself, all right, I have this reaction mixture that has 8 H2s and 2 N2s. Let me do the math on the side here. I like doing the math. 8 moles of H2 for every, let's see, 3 moles of H2, I'll get 2 moles of NH3. So if I do this math, I get 8 times 2, which is 16, divided by 3. I will get 5.33 moles of NH3. Okay, good to go. If I do N2 now, if I have 2 moles of N2, this is a 2-to-1 ratio. 2 moles of NH3 for every 1 mole of N2. I will get 4 moles of NH3. Now, what am I doing? Let's see if you are doing this all together. You remember, I'm trying to figure out which of my reactants here will give me my least amount of product, and I only have NH3 as my product. It looks like my N2 is limiting how much product I could make. I could only make 4 moles, or I could say 4 molecules of NH3. So I have to find which of these reaction mixtures has at least 4 of them. Well, the answer is not going to be A, because I only have 2 in there, not 4. Now I'm left with B and C as one of my answers. Well, my limiting reactant is the one that limited how much product I could make, N2. It looks like my excess is H2. Now, let's combine these now, knowing that I'm going to make 4 of them. How am I going to do this? Well, for every 1 N2, I need 3 H2s. So I'm going to circle them. 1 N2 and 3 H2s. This is going to give me 2 NH3s, right? If I combine 1 N2 and 3 H2s, I'm going to get 2 NH3s. Can I do this again, kind of like my sandwiches, where I combine let's pretend like the N2 is the bread and then your H2s are like your meat and cheese. Can I do this again? And the answer is yes, I have another N2 that's going to be completely used up. Look at this. I can make another 2 NH3s. So altogether, I'm making my 4 NH3s, and I actually have some things that are left over. I have these 2 H2s that are left over. So I need to find an answer that I'll have 4 NH3s and 2 H2s left over, and that is choice C. This is just like a basics quiz question that you will get in the beginning of the year. You will have to look at a particle diagram and combine these particles and figure out what's going to be left over and what's going to be completely used. Look, notice my N2 is completely used. I don't have any leftover. I'm going to say completely. Completely used. I have no leftovers whatsoever. All right, so now I'm going to bring us back to a BCA table. You may recall that in a previous lecture, I introduced you to a BCA table, and one of your exercises, I believe exercises 11 and 12, ask you to use a BCA table. BCA tables are great for regular stoichiometry, but BCA tables are the best for limiting reactant problems. I promise you, if you use the BCA table for limiting reactant problems, you're going to do yourself a good favor. So let's look at an example here that's going to be limiting reactant percent yield. So a reaction mixture contains 42.5 grams of magnesium, 33.8 grams of O2. What is the limiting reactant? Now I want you to notice something. How do I know this is limiting reactant problem? 2 amounts of reactants given. If I have 2 amounts of reactants given, this is automatically a limiting reactant problem. And I have to think, okay, which of these reactants is going to give me my least moles of product, right? So I'm going to go all the way back to this now. I have to figure out what my limiting reactant is and do setup like this, where I do like a mole-to-mole ratio and figure out which of my reactants is going to give me my least moles of product. So let's go back to it. Now, I'm going to put all of this information in a BCA table. Our chemical reaction is 2Mg, right? And that's coming from right here. I don't know if you could see it. It's kind of hidden between the information I tried to throw here. But we have 2Mg plus O2, 1 O2, to give me 2 MgO. That's nice. I have simple 2 to 1 to 2 ratio math that I could probably do quickly in my head or know what math I have to do. Before, well, I have 42.5 grams of Mg, and I have 33.8 grams of O2 before. Do you remember what I'm going to put before for my MgO product? Well, before the reaction starts, I'm not going to have any product, 0 moles. So we're good to go. Now, remember, in my BCA table, only use moles in BCA. So I am going to convert these grams to moles. If I kind of put the molar masses here to kind of help you out. The molar mass of magnesium, that's the element. If you look on the periodic table, I know I haven't gone back and forth too much, but I will for a second. Right? Here's the periodic table. Sorry. Here's the periodic table. Again, the molar masses are right here. If I wanted to get the molar mass of MgO, it would be this molar mass of 24.3 plus this molar mass of 16, and I get 40.3 grams per mole. That is the molar mass of MgO. Molar mass of Mg is 24.3. Molar mass of O2 is 16 times 2. I know I didn't get a chance to go back and forth for this, but I want to make sure you know how to calculate a molar mass. You will need to know how to do that. All right, so let me go back now. All right, so now I'm over here. I gave you the molar mass of Mg is 24.3. If I do 42.5 divided by 24.3, I will get how many moles of Mg I have. So I'm going to put that on a calculator on the side here. 42.5 divided by 24.3. I get 1.75 moles of Mg to start. And now notice how I'm not going to put an excess in the other reactant here because I have a quantity. I have 33.8. I'm going to divide that by the molar mass of 32. I have 1.06 moles of O2 to start. Now, watch what I do here. I'm not going to fill out the reactants change yet because I don't know which of these reactants is limiting. I'm going to split my product line here. This is going to be from Mg, and this is going to be from O2. Let's see if you could see how I'm doing a little bit of mental math here, or just kind of visualizing it. For every 2 moles of Mg, I will get 2 moles of MgO. That's 2 to 2, which is 1 to 1. So if I have 1.75 moles of Mg, that means I should get 1.75 moles of MgO. That would only be if Mg was my limiting reactant. But what about O2? Well, if I had 1.06 moles of O2, I had to ask myself how many moles of MgO could I make? Well, this is a 1 to 2 ratio. I have 2 times the amount of MgO as I do O2. So I'm going to multiply this by 2. 2.12 moles. I would get 2.12 moles of MgO if O2 is limiting. But I have to ask myself, which of these numbers am I going to choose? Choose lowest moles. Between 1.75 and 2.12, I'm going to choose 1.75 moles of MgO are going to be produced. Now, if you can't see that here, I'll quickly do the math on the side here. 1.75 moles of Mg and 1.06 moles of O2. I'm going to do the mole ratio stoichiometry math, right? So for every 2 moles of MgO, there's 2 moles of Mg. Oh, would you look at that? That math comes out to 1.75 moles of MgO. For every 2 moles of MgO, there's 1 mole of O2. Look at that. I'm multiplying by 2. I get 2.12 moles. Sorry, that should say MgO. Of MgO. And then which do I choose? Choose lowest moles. That means Mg is my limiting reactant. If that's the situation, it gets completely used up. Remember, my limiting reactant, like I did in the example here, my N2 is limiting. It is not left over. It's completely used. I'm going to do the same thing here. That means my Mg is going to be 0 after, which means I'm going to use all 1.75 moles of Mg. I'm also going to shade out this 2.12 so you don't see it anymore because it's not the correct answer. Now here's where I got to figure out how much of my O2 am I going to use. This is the first time we're going to look at excess now. Right, so if I have 1.75 moles of Mg, I need half the amount of this for O2. 1.75 divided by 2, 0.875 moles of O2 are required. And I have 1.06. I have plenty. So if I want to figure out what my change is, then that's 0.875, I could calculate my excess. 1.06 minus 0.875, and I get 0.185 moles of O2. This is my excess. I have 0.185 moles of O2 in excess. I have 0 moles of Mg because it's completely used, and I have this many moles of product that are made. I'm going to go ahead and convert this 1.75 moles of MgO into grams because I might need it for the next part of this question. The molar mass of MgO, I already told you, is 40.3. So moles times molar mass. This is going to tell me my theoretical yield in grams. So 1.75 times 40.3. And I get 70.53 grams of MgO. This is my theoretical yield. Excuse me. This is how much I should get. Excuse me. This is how much I should get if I do the calculation. This is theoretical. And I calculated it. And this is just like earlier where I go, okay, which of my reactants gives me my least moles of product? I'm going to use those least moles of product as my theoretical yield. That's how much I should actually get. That's how much I should theoretically get. And look at this. Suppose that after the synthesis, the actual yield is 55.9 grams. What's the percent yield? Remember, actual over theoretical times 100 equals my percentage. So my actual is 55.9 grams. My theoretical is 70.53 grams. If I multiply by 100, I will get 79.3% yield. Higher than the last calculation. And we're done. Now, I know I did a lot of work here, but I'm teaching. I'm trying to show you all of my work, right? Some of you might be able to do the 1-to-2 ratio very quickly by multiplying or dividing by 2 because you recognize that this is a 2-to-1 or a 1-to-2 ratio. Use that, and it could help you kind of get to the root of solving the problem for the limiting theoretical actual. Okay? All right, let's do another one, right, where I have the BCA table, right? So ammonia can be synthesized by this reaction, 2NO. I'm going to just start writing it, plus 5H2 yields, sorry, this needs to be split, yields 2NH3 plus 2H2O. Cool. Starting with 86.3 grams of NO and 25.6 grams of H2, find the theoretical yield of ammonia in grams. So I really care about ammonia. I'm going to split this little box here in half so I could do that calculation all over again. I'm going to use a different color now. All right. Remember, BCA is only moles. So if I have 86.3 grams of NO, I gave you the molar mass as 30.1. So 86.3 divided by 30.1. And I get 2.87 moles of NO. I'll do the same thing for H2. The molar mass of H2 is about 2 grams. So 25.6 divided by 2 grams per mole. I got 12.8 moles of H2. I don't know if it's obvious which of these might be my limiting or excess, but we'll see, right? Before the reaction starts, I don't have any products, right? This is our before. This is usually given. Before the reaction starts, I have no products before the reaction. Now, we don't really care about H2O, so I'm going to focus on the NH3. Let's look at the molar ratios here. For every 2 NO, there's 2 NH3. Let's say from NO and then from H2. If I was going from NO to NH3, if I was going to use all of my NO, I should get 2.87 moles of NH3. It's a 2-to-2 ratio, which is essentially 1-to-1. What about if I were to use all my H2? This is a 5-to-2 ratio. Some of you might realize that I'm going to have to divide by 2.5. So I'm going to do that. I'm going to say 12.8 divided by 2.5. I get 5. Oh, goodness, I'm sorry. I get 5.12 moles of NH3 if it were coming completely from the H2. We could already see right now that 5.12 is too large. We're going to see that 2.87 is how many moles of product I'm going to make. My NO limits how many moles of product I could make. And I am done. I'm going to use all 2.87 moles of NO. I'll have 0 left over. If I wanted to get the excess, or if I wanted to figure out how much H2 I'd need, I mean, it's a 2-to-5 ratio. I'd have to multiply this by 2.5. So 2.87 times 2.5. 7.18 moles of H2 is only required. 12.8 minus 7.18. And I get 5.62 moles of H2 in excess. But it didn't ask for it, but I'm doing it anyways. It didn't even ask for H2O, and I'm going to let you know it's going to be the same. It's also 2 and 2, so it'll be the same ratio. It wants the answer in grams, so I'm going to convert 2.87 moles of NH3 to grams by multiplying by its molar mass, which is 17. 17 grams per mole. So I'll have 2.87 times 17. And I'm going to leave it at 48.79 grams of NH3. Boom. That is my theoretical yield, and we are done. Okay? All right. I'm actually going to skip example number 4. You could do example 4 for, let's say, it's extra credit. Or I'll just call it, in AP Chem, we call this help. This could replace some missing points in your summer work if you do it. All right, so I'm going to skip this, but if you do want to check your answer, I do have the answer off to the side somewhere. If you do want to check your answer to this one, you should get 80.8% yield is the percent yield. If you get that yield, you're going to answer and do all the parts of the question correct. So this is the answer. All right, and that ends our last lecture here. This is probably our last big lecture for the summer and our last big lecture for the summer work part 4. I'm going to remind you again, you're going to do exercises 13 through 19. I did do some work. For 13, I gave you the answer, and for 14, I wrote a little bit of notes here. You could feel free to pause and write this and copy it down so you get on a roll or the ball of what you need to do. All right, so for 13, you're just doing straight up like molar ratio and figuring out which one limits how many product I could make, and that's my limiting reactant. 14 is another particle diagram and thinking about which reactant's going to make more product. 15, 16, 17, and 18 are all like the last two questions that we just did. You could feel free to use a BCA table if it helps, or do all the work that I've shown in an earlier example. For 18, I kind of tried to help you out with, some of us had to remember all the way back to the part 1 information with density. If I do density times volume, that's going to give me my mass, so I just did that for you already. And then finally, 19, this is AP style thinking. This is particle diagrams. Think sandwiches too. This is kind of like I give you a particle diagram and I give you amounts and I want you to figure out what my product's going to look like. We did this like with the ammonia synthesis and we did this with the sandwiches. Alrighty, that's all. I want to remind you to do the preparing for basics quiz. You don't have to turn those in, but again, we're going to use these preparing for basic quizzes to review for our basics quiz. I would really highly suggest that you do these problems. If you could do these problems, you could guarantee that you could understand how to do the problems for the basics quiz. And that is all. If you have any questions or concerns, you could feel free to email me or message me in the Remind, and I could try and reach out to you as soon as you possibly can.